Hey, Vince Riley here, CFI, double I, rotor wing, and fixed wing. Today's topic is going to be airspace. Whether you're getting ready for your private pilot check ride, preparing for a biannual flight review, or just want to brush up, this video will not only give you an easy way to remember which airspace is where, but will also help you remember your visibility and cloud clearance requirements. The designation of and altitudes of airspace we'll cover can be found in FAA Regulations Part 71. The first airspace we'll talk about real quick really doesn't apply to VFR flight. That's Class A airspace. And it begins at 18,000 feet all the way up to flight level 600, which is basically 60,000 feet. To fly into Class A airspace, you have to have an IFR clearance. Next, we'll talk about Class E airspace. A good way to remember where E airspace is to just remember it's everywhere, from the bottom of Class A airspace all the way down to 1,200 feet AGL all across the United States, with a few exceptions, and around some airports which have approach procedures. It goes down to 700 feet AGL. Everywhere below Class E airspace, starting at the surface, is Class G.
Don't be overwhelmed by this. Don't be overwhelmed.
About Class E
This comes together.
airspace is there's a delineation at 10,000 feet MSL, which changes visibility and cloud clearance requirements. All the cloud clearance and visibility requirements can be found on a chart in section 91.155. Here's an example of the chart. Basically, I just cut off the bottom half, which is where most of the confusion comes from when talking about airspace and cloud clearance requirements. So we're going to talk about it for a moment because this is where most people get confused. To begin with, there's a small section for helicopters. Well, they're a special kind of people, bless their hearts, so we're not going to talk about that right now. Below that is another section, which is a remainder of the days gone by, that talks about more than 1,200 feet above the surface, but less than 10,000 feet MSL. And as far as I know, I haven't been able to find any of these areas on the current VFR sectionals since 2017. So, for now, just ignore it, and what I want you to remember is Cessna 152. We're going to talk about that in just a minute. The next area below that talks about being more than 1,200 feet above the surface and at or above 10,000 feet MSL, again, I know of no areas where this applies in current VFR sectional chart. The thing I want you to remember here is F-111, as in F-111 aardvark bomber. Additional confusion about Class G airspace comes from the chart supplement guide and current charts, which still show shaded blue areas in the legend and talk about Class E above 1,200 feet AGL. Again, I haven't been able to find that on any of the modern maps. As you'll see in the current VFR sectional charts, it's the shaded magenta area. That's where it goes down to 700 feet. If you're feeling nostalgic about the old days, here's an example which comes from the Salt Lake VFR sectional from 1971. It shows both magenta and blue designated Class E areas. There were actually VFR corridors above 1,200 feet in other areas through the mountains.
Don't worry about that. We're going to talk about the magenta and the blue, what that
Again,
means.
those have all been removed from the map. If you can find one, please put it in the comments below and let me know you found it. Since I already showed you the chart from Part 91, I want to talk about Class G airspace first. At some point in your flying career, you're probably going to hear a question that sounds a lot like this. Your DPE or instructor will point to a spot on a VFR sectional and ask, what is the visibility and cloud clearance requirements when your brother's cousin's aunt, 3 times removed, is drunk flying her grocery cart VFR at 10,100 feet? This is an easy question, and here's how you'll remember it. Anytime you're less than 1,200 feet AGL, regardless of the MSL altitude, your visibility requirement is 1 statute mile clear of clouds. And at nighttime, it's 3 statute miles visibility with basic cloud clearance. And we're going to talk about what basic cloud clearance is in just a minute. So we don't need to talk about cloud clearance and visibility requirements in Class A airspace because that's only for IFR traffic. So remember, Class E airspace is everywhere down to 1,200 feet AGL and around some airports down to 700 feet AGL or the surface. So now let's add in our Class G airspace, our Class C airspace, our Class D airspace,
This will come back around a
and
bunch.
Class
But
B
this is-
airspace, and our surface
These are
area,
the pictures
Class
basically
D.
of what the different numbers of the type of airspace it covers. So we'll come back around many times on this, but pay attention.
Let's add a few clouds because we're going to talk about our visibility and cloud clearance requirements. First, we'll talk about Class E airspace above 10,000 feet MSL. And remember, I said to remember F-111.
F-111 is a type
So
of
above
airplane.
10,000
It's just
feet
an acronym
MSL,
to
your
remember.
visibility requirements is 5 statute miles. While cloud clearance requirements, these were the ones come from in the F-111, 1,000 feet below, 1,000 feet above, and 1 statute mile horizontally. F-111 is 5 mile visibility, 1,000 below, 1,000 above, and 1 statute mile horizontal. So below 10,000 feet MSL is where we get Cessna 152. And this applies to all controlled airspace below 10,000 feet MSL with one exception, and we'll talk about that in just a minute. Below 10,000 feet, you're required to maintain 3 statute miles visibility and basic cloud clearance. The C in the Cessna 152, the third letter of the alphabet, help you remember the 3 statute miles. Cloud clearance is 500 feet below, 1,000 above, and 2,000 feet horizontal. Again, that's where Cessna 152 comes from. This cloud clearance is referred to as basic cloud clearance. That's how you're going to remember your visibility and cloud clearance requirements below 10,000 feet MSL. You just have to remember where to put each of the numbers. The Class G airspace visibility and cloud clearance requirement during the day is 1 statute mile clear of clouds. At night, it's Cessna 152, just like the rest of the control aircraft. 3 statute miles and basic cloud clearance. So what do you think the visibility and cloud clearance requirement is in the Class C airspace? That's right, Cessna 152. So what do you think the visibility and cloud clearance requirement is in Class D airspace? You're right again, Cessna 152. So what do you think the visibility and cloud clearance requirement is in surface E airspace when it's active? That's right, Cessna 152. So what do you think the visibility and cloud clearance
We'll cover this many more times, but let me give you also a brief before this to show it makes sense. Class A is above 18,000 feet, so we're not going to worry about that anymore. But Class B, this would be the big airports of the country, the SFOs, LAX, Atlanta, Chicago's, and New York's. And we'll talk about Class B airspace and those requirements. But that's what that's referring to without telling us. Class C airspace would be the space around Fresno, Sacramento's, San Diego's, you know, not as big. And so they have requirements for visibility and some other requirements too, but just so, because he's talking about the weather requirements, he's not really gonna tell you what those mean. I just want to insert that for you to have kind of a clue what he's, reason he's talking about it. Then here, this G, without making you memorize it right now, this is the low stuff. 700 and below 1,200 feet. So even like right here, below 1,200 feet, we're in this case, it's 700 feet. It's either 7 or 1,200 feet. When you're flying around super low, you have a reduced requirement for visibility. So think of G as just very low. E is most everywhere, as he said here. But most of the time, if you don't know where you are, it's mostly E space. This is outside of the big cities. And D is a towered airport. Any towered airport like Livermore, Modesto, Stockton would be a D. But San Francisco, the other ones would be a Bravo. And we actually get into, we don't really say D and C. Bravo airspace, Charlie airspace, Delta airspace. But we don't call this Golf or Echo, it's just G and E for some reason. Okay, so the basic cloud clearance number, that's an important one. This is a recurring, 1,000 above the clouds, 3 miles visibility, and 500 below. So that's kind of a number that you're gonna hear many times, basic cloud clearance.
What does MSL mean?
Mean sea level.
Okay.
So AGL, oh, that's a great question. AGL, which is what these are, above the ground. Because obviously,
Right.
you know, as the ground moves, of course, you
Okay.
don't always know exactly what that is. But you do know we're
Okay.
10,000 MSL because your altimeter, you're not looking down and guessing at it.
Right.
It's based on.
So MSL is just from sea level, and
Yes.
AGL is how far you are from the ground.
Yes, and mean sea level will be more like what we're reading on altimeter when we get into altimetry.
Okay.
And then above the ground, you would actually have to do your arithmetic. In other words,
Okay.
you know, in other words, if this is 2,000 feet, which we are here, 2,700 feet becomes Class E.
Okay.
But that will come around, great question. Any others?
Requirement is in Class B airspace. Well, here's the exception. It's still 3 statute miles, but it's clear of clouds. In other words, you can be a foot outside the cloud and meet the requirements for Class B airspace. The reason for this is because to enter Class B airspace, first of all, you have to have a clearance. And second, they'll tell you to maintain VFR. And lastly, you have a transponder with ADS-B. So they will know exactly where you are to keep you clear of IFR traffic and to give you traffic advisories. It's really that simple. In controlled airspace below 10,000 feet MSL, it's Cessna 152. 3 miles visibility and basic cloud clearance, with the exception of Class B airspace, which is clear of clouds. In Class G airspace at night, it reverts to the same requirements. So really, you only have to remember F-111, Cessna 152, and then 1 mile clear of clouds during the day for Class G. And then,
Not to confuse that, sometimes we do little reminder things for our brains to work. The Cessna 152, does everybody know what that is? What a Cessna 150 is? Pretty common, real common trainer. So he's not trying to confuse you. You don't have to know what a 152 is. It's just a memory device. An F-111 was a 70s, 60s whoopie-zoomy Air Force fighter that everybody knew, with the first swing wing thing. So most people kind of know what that is. He's not trying to tell you. That's the only reason he's using these is reminder, little mental reminder things. So don't get too caught up in that.
Class B, again, clear of clouds. So let's test what we've learned. Let's say you're right here at 800 feet AGL. What type of airspace are you in, and what is your visibility and cloud clearance requirement?
Remember he said 7? Yes.
If you said Class G airspace, you're correct. And
What
your
you said,
visibility and cloud clearance requirements during the day? Right, 1 mile and clear clouds. How about for night? 3 miles and basic cloud clearance, 500 below, 1,000 above, and 2,000 horizontal. Okay, well, what if you're right here at 3,600 feet in SL? What type of airspace are you in, and what are your visibility and cloud clearance requirements? Remember, the VFR sectional tells you just about everything you need to know about controlled airspace.
This is a pretty tricky question for this flight because this is a tower. From last week, we know the Blue Airport's here, is Tower Airport, and that segment of circle there indicates that's the Class D, and that's the Class D from this tower. There's a bunch of towers right in here, control towers. So the Class D is the question. You didn't really say that, or you did.
The bottom of the Class B airspace in this area begins at 7,000 feet. The top of the Class D airspace ends at 3,500 feet MSL.
When you get into maps, cover that some more.
If you said Class E airspace, you're right. And your visibility and cloud clearance requirements? That's right, 3 miles and basic cloud clearance. How about if you're right here at 12,000 feet MSL? What type of airspace are you in, and what is your visibility and cloud clearance requirements? That's right, Class B airspace. And your visibility and cloud clearance requirements? I hope you said 3 statute miles visibility and clear of clouds.
So remember how we said
Let's
that,
look at a
this
few
comes
more
back to
examples.
3 miles and basic cloud clearance. That's 500 below clouds.
What if you were here at
1,000
5,100
above, 2,000
MSL?
this way.
What class of airspace are you in, and what is your visibility and cloud clearance requirements? Remember, the VFR sectional is very helpful and shows the top and bottom of this Class C airspace. Correct, Class E airspace. And what is your visibility and cloud clearance requirements?
At 52 to 8, that means that's the Class C. It's an upside down cake.
Correct again, Cessna 152, 3 statute miles visibility, basic cloud clearance, which is 500 feet below, 1,000 feet above, and 2,000 feet horizontally. All right, one more example. What if you're right here at 11,000 feet MSL? What class airspace are you in, and what are your visibility and cloud clearance requirements? Now you're getting it. Class E airspace above 10,000 feet MSL. And the visibility and cloud clearance requirements? Remember, F-111, above 10,000 feet MSL. 5 miles visibility, 1,000 feet below, 1,000 feet above, and 1 statute mile horizontally from any clouds. If this was helpful, please hit the like button, subscribe, and leave your comments below. I'll also provide a link for 2 other videos.
Don't be overwhelmed by this yet.
Determining your position
Because
using a VOR
you're an
and
instructor when you're
road
flying,
path.
when you're
Those are
doing
other
cross
areas that
country,
people
you'll start
struggle
really
with.
putting it together.
Also,
This
if you'd
is-
like another topic discussed,
You
you
will
can
know
leave a
this
suggestion
stuff.
in the
It
comments
takes a
below,
lot of-
and I'll
lot
try to
of
make a
heads.
video for that too.
Okay, good. Okay, any questions off the top of your head? Lots of them, but.
Yeah.
So the real important takeaway on that is the basic cloud clearance, BCC. So in Class E airspace, the basic number that we do want you to take away from tonight is 3 miles visibility. And the Cessna 152 that he's referring to is when there's a cloud. It's all hypothetical. If there's just this little one little puffy cloud with a
Right.
nice edge. And it's not like that, you know, it's a hazy cloud, and we're talking about clouds. But hypothetically, you've got this one perfectly round little cloud, okay? And you're 1,000 above, 2,000 feet horizontally, 500 feet below. So that's the number I want you to remember, okay? 1,000 above, 2,000, 500 below, and 3 miles visibility. Again, on this perfect day with this little, it's not
One
always like
cloud.
that, but that's the number you need to take away
Yeah.
from this page, okay? And so again, he gave us different examples. Class D, that was a tower there. And then he went up above Class E, which is pretty rare. You know, I mean, if you're flying over a 10,000 foot mountain, if you're close to the ground, you're close to the ground. When we're flying 10,000 feet most of the country is why, and the logic, if it helps you, is airplanes go faster above 10,000 feet. Jets have no speed limit. Everybody has a speed limit of 250 below here. And we're doing like 80 and 90 miles an hour flying around. So when you get up high, they want bigger numbers. Does that make sense?
Hey, Vince Riley here, CFI, double I, rotor wing, and fixed wing. Today's topic is going to be airspace.
Whoops.
Whether you're getting ready for your private pilot check ride, preparing for a Hey, Vince Riley here, CFI, double I, rotor wing, and fixed wing. Today's topic is going to be airspace. Whether you're getting ready for your private pilot check ride, preparing for a biannual flight review, or just want to brush up, this video will not only give you an easy way to remember which airspace is where, but will also help you remember your visibility and cloud clearance requirements. The designation of and altitudes of airspace we'll cover can be found in FAA Regulations Part 71. The first airspace we'll talk about real quick really doesn't apply to VFR flight. That's Class A airspace, and it begins at 18,000 feet all the way up to flight level 600, which is big. Hey, Vince Riley here, CFI, double.
Hey, Jake. Yep. Mayday. Did that one. Yeah, let me go back over that airspace, which I was interrupting there a little bit, because that was a lot to mention. So. Again, Class G, well, Class A we're gonna forget about, that's above 18,000 feet. But, and that's MSL number. Bravo, Class Bravo, the big airports. Class C, the medium-sized airports. Class D, towered airports. Even
So,
though, yeah.
was like LAX classified as Class B just because that has a tower on it?
No, it is a Bravo. Every one of these Bravos will have a tower.
Okay.
Every one of these Charlies will have a tower.
Okay.
But,
There's only 12 Bravos across the country.
Yeah.
It's a real big city.
yeah, the New York, Chicago's, Atlanta, San Francisco, 2 in California, San Francisco and LA. C is a lot more common. Okay, then, so G, as we look down here, it says 700 feet and 1,200 feet. Just kind of remember that for now, like 700 feet would be, this airport right here to 700 feet is G airspace.
Okay.
So, mile and clear of clouds.
So above this airport.
Above 1,200 feet, or above 700 feet, we're into E. So by default, like he said, E is mostly everywhere, okay?
Okay.
Go to the rest of everything. Non-towered airport with an instrument approach, that's what we have here, for example. This is a non-towered airport, but there is an instrument approach to here. So it's gonna be, non-towered with an instrument approach is gonna be 700 feet above the ground. And the rest of everywhere is 1,200 feet. So G and G. And, we'll come back to that a lot. Yeah, the Class Cs, as we were mentioning, in this case you're using Las Vegas, requires radio communication. Whereas we can fly around this airport, around this E airspace that we're talking about there, we don't even need a radio, we don't have to talk to anybody.
Oh, really?
Correct. But in Class C, you need to talk to somebody to go in or through it.
Okay.
Same with D and B. And we'll get into those specifics. This is weather day. Let me see what else it says there.
MSL is C. It's New York sea level.
The sectional charts that we were using last week, that's a terminal chart right there. Dave's got a sectional here. Caitlin, you have your sectional?
Yeah, I do.
I guess, helps though, they're saying that they don't technically have to be, but we put out
That's just like a real
stock
close up
view
view
right there.
of a terminal.
Yeah.
So this covers all your forests.
Let's go to stock. Let's work on this one. So we're looking, let's find Class D. And the first clue for Class D is, Dave, how do we know we got a Class D? Delta.
I don't remember.
Remember a blue airport?
Oh, the blue.
So any of these blue airports is a tower, a control tower. And that is when the control tower is open, that's Class D. Okay, if the control tower is closed, it's not a Class D. But see the segmented, blue circle around it?
That's just blue.
Yeah, see how there's a broken blue? That's the D, and it'll be different shapes at different places. We're all around here, but they're not always around, like,
Kind of like on that picture.
yeah, they can be different
It's not-
shapes.
It's
for
not
dark and
circular, it's got that little
And then,
keyway on it.
see that example, it's a keyhole for the instrument there. And the 2.7 would be the top, because it's not always the same. Most of them top at 3,000 feet, but see that box number there? See that box number there? That's the up to. Sure. See that, Dave? So each of these Ds, class deltas, well, that's a Charlie
Yeah.
right there, okay. But there's a class delta,
Okay.
and that's the top. See that box number?
Yeah.
Means it goes up to 2,000.
Oh, okay.
See that? Find me a tower airport like this. See that box there? 26. Yeah, that's the top of this D. So that's a cylinder like that, with 2,600 AGL on the ground. Okay? So, where's the top of the D at this airport? And in blue, according to last week, that means it's a tower. Yeah, blue room is, so these magenta ones means there's no tower. And then class C, there's a C, see the magenta circles? They're not always exactly circles, but that's a C, that's a C, Monterey, Oakland, San Jose, Fresno, Sacramento.
So it's not for you to work on.
Right there. It's the bottom, so it's like, these like upside down cake.
That's the reason for.
It's like an upside down cake, it goes up like that.
That's the way it should have been.
And it'll usually say the top, right? Surface to 4,400 feet. And it's surface to 4,200 feet. Surface to 4,000 feet, okay? You got that on class C? There you go, that's the legend is always a great place to go, that's not cheating for a guy, you wanna know all that.
No,
That's why you want
that's,
to see.
that applies to the airport. Not necessarily.
Class Charlie's. Open that up a little bit, it's on there. So here's the class Charlie.
Yeah, it's still kind of like this.
And the top and bottom surface,
Chunks of
4,400 feet.
Chunks of
Then there's an outer ring here, and there's another number.
There's nothing over here, it's bigger before. This C, which goes.
Yeah, 44. So you could fly under this, 2,400 feet, and it's not in the C. Then you're in just this E.
Not
Okay.
okay.
Use everything
But
else.
generally, that's it.
Got that? Sam? Fly up the C. Yeah, just here. Here.
And there are. So you have to call. Upside down wedding cake almost. That's what these different surfaces are. So imagine it as that wedding cake that gets taller, right?
It's upside down.
Yeah. So this one, it's marked right here all the way around here.
See our upside down cake here?
To be up here, you have to be right up here. So you
C
can
usually has these two steps.
You can actually be.
And class Bravo usually has maybe 4 or 5 of these. We call
But
those
that's,
down
but that's
cake
the
because
distance. That's certain.
it goes up, it's usually less than 30 miles. It's usually about 25. And class Bravo is almost always,
Bottom, 6,000.
I'm gonna say,
So in this segment.
I'm gonna say always, but I'm not
which is
certain,
follow the segment.
top at 10,000 feet. Like Denver has one, since Denver's already 5,000.
Ready to go there?
Yeah, it tops at 10,000 also, so it's smaller this way. And for your class deltas, your Charlies and Bravo, what they all have in common is you have to get a clearance.
This is the airspace
To be-
between
be in
6,000
there.
and 10,000 feet.
Okay.
So if you're at 8,000 feet right here.
The actual clearance is different.
And the reason for that is.
And when we get into
the
that-
airliners are going down.
We'll get into that.
And you get clearance, that's from radio
Yeah,
communication.
and you have to get clearance to enter. See airspace, you have to, you have to read back the tail number. And then you got the space. See this space, that is. Is that altitude?
Okay, where else did I started here? Generically, this is always low. If you don't know, basically, this one here is basically E. But below, 1,200 feet, G, 1 mile visibility requirement. We're down to clear clouds. Well, not the purple numbers, generically, we're gonna pick a spot that's between the surface, right here. Right here, it's G, round clear clouds, below 1,200 feet. When you go inside, when that magenta fades in, it's 700 feet above the ground. We'll talk about that in a minute. But below 700 feet above the ground, all you need is a mile from clear clouds visibility. And what that's really telling us is, for you later, there's an instrument approach with your control tower. And our airport here is one of these that's like that. It has no control tower, but there's an instrument approach. It happens to come here this way. Yes, so these are our airports. And a mile of clear clouds, that's pretty low visibility. I mean, that's like being able to see, that hill's a couple miles away.
Right.
I mean, you can't see anything. A mile, that's nothing. If you got a fast airplane, you're in deep blue, you don't want to, but that's the minimum. And you could, but you might want to just fly around the patch, you know, in the 172 around the airport. A mile's enough because you're going round and round. You know, it's a little scary, not a good idea. You can't go anywhere else. But, okay. We move on.
Well, every one of these is different.
Right, okay. Oh, okay.
I mean, the airspaces have certain.
So we're gonna talk about that,
So this is C airspace.
where E
C
transitions to,
C
where
airspace.
G on the ground transitions to E, is 712 and 1,200 feet, 700 feet and 1,200 feet. That's very
The
complicated.
chart here just
So,
telling you.
what we were just telling you is inside that magenta, that's lower, 700 feet on up is E. But, generically, most other airspaces, like here, just everywhere, it's nothing inside of there. It's 1,200 feet is where G starts, 1,200 up to 10,000. I'm sorry, did I say that? I said that wrong. E.
Yeah.
Did I say G? E, I'm sorry, everywhere.
Right.
If that was your weather.
Thanks.
Your weather was.
Good catch.
Probably not safe for you to navigate the rest of the state. That's intended for.
So the most important one, just for tonight, is the basic cloud cover, BCC. It used to be referred to as basic VFR.
All this
A lot of your instructors will call it basic VFR, meaning there's a cloud, you need to be at least 500 feet below it, 1,000 above it, 2,000 and 3 miles visibility. That's the one takeaway you want to know tonight. The mile clear clouds down low. The over 10,000 feet, we're going to let you forget about that now. That's kind of you're not going to be there for a long time. Okay, yeah.
That was the weirdest thing, once he was on one of my flights, having
The Central Valley here is
Yeah.
generally
actually happy to do that.
Yeah.
They were solid outfit.
Well, what's nice is when you can have a cumulus cloud that you look at that. Our clouds aren't always just a puffy white thing, as I was saying before. They can be very nebulous. Well, let's not use it. That's not a type of cloud, you know, we're gonna talk about types of clouds here in a minute. But, a cloud isn't always just a puffy thing.
Yeah.
You can't see where you are.
500 feet.
Well, that's a cloud. You might not have a type, but you can't see where you are if you don't have visibility. In this case, 3 miles visibility, you're not supposed to be there, you need to turn around.
From the surface.
Or you shouldn't have been there. And that's why you wanna know what the weather forecast means to you, because you don't want it to come in around
So
you.
since the case is that the Central Valley is about 1,000 feet, if you're at 2,600 feet, and that's out.
A little lighthearted comedy, 2 minutes.
Tell me about what happens on landing. On landing, what happens if it's going too fast?
They say, go around, go around. The pilots go full power, then they take off again.
Okay,
After that, they go around for another approach.
okay, wow. All right.
Then, the emergency exits change all the time.
Uh-huh.
They could turn into slide or raft slide.
Oh, wow, cool. And why would we do that? Why would we use the slides or rafts?
Because of emergency landings.
Oh, wow. What else do you know?
I know about altitude.
Oh, really?
Yeah.
What do you know about altitude? Tell me.
What I know about altitude is that if a plane is descending or climbing, it goes into clouds.
Oh, okay, okay, wow.
And
Ah,
I also know that an airplane has an APU.
an APU.
Yes,
Oh,
right
wow.
there.
Can you point it out to me? Can you find it? The switch for the APU?
Yeah,
Where?
right there.
Oh, wow. Yes. That's in case the APU has a fire, but this is the APU switch, right?
Yeah.
Bless you. Bless you. Bless him. He knows a lot, huh?
Also, some planes have a ram air turbine.
A ram air turbine, Adam?
Yeah.
And what does that do?
It gets emergency systems back on if the engines fail.
Okay.
Then the ram air turbine can help to bring back the systems.
To bring back the systems to control the aircraft.
Yeah. But due to the no engine power, the landing gear doors will not come up.
Okay. Okay.
After that, you have to do something else to lower the flaps.
Oh, you have to do something else to lower the flaps?
Yes.
Okay.
You have to lower them by gravity alone.
Oh my goodness.
When we're doing our homework, it kind of comes out.
He's older than me, that's for sure.
Weather. Whether you love it or hate it, we have to fly through it. Might as well learn what makes it happen. Our atmosphere is composed of 78% nitrogen, 21% oxygen, and then 1% of carbon dioxide and other trace gases. As we go up in altitude, that concentration stays the same, but the pressure decreases. Our atmosphere is split up into 4 different layers, starting with the troposphere, and that's where most of the weather happens. In the troposphere, temperature decreases about 2 degrees every 1,000 feet, and the pressure decreases about 1 inch every 1,000 feet. Now at the top of the troposphere, we have the tropopause, and that's kind of a lid or the top of the troposphere, and that's where jet streams happen. The tropopause also varies with latitude and with season and temperature. Next we have the stratosphere, and there's little to no weather up there unless some severe thunderstorms punch up into it, and it goes up to about 160,000 feet. The mesosphere and the thermosphere are up next, but there's no weather up there, plus we can't get up there to fly anyway, so we're not going to talk about those two. All weather that we have is due to uneven heating of the Earth's surface. Looking at this picture, you can see that the same amount of sunlight at higher latitudes gets distributed over a much bigger area and doesn't heat up the surface as much. If you remember from astronomy class, our Earth is tilted about 23 degrees. So in the summertime in the north hemisphere, the Earth is tilted closer to the sun and gets more concentrated sunlight further north. And in the wintertime, the Earth is tilted away from the sun up north and gets less sunlight. Once again, all weather is due to the unequal heating of the Earth. Now we all know that warm air rises, like steam from a boiling pot. But why is that? As air warms up, the molecules expand. And when they're expanded, they're a lot less dense and they're lighter than the surrounding air, and so they rise like a helium balloon. And as air cools, it becomes denser and heavier, and it sinks back down, replacing the rising warm air. At sea level, a column of air going from the surface all the way out into space weighs about 14.7 pounds per square inch. As you go up in altitude, it's about half of that at 18,000 feet, or 7 pounds. We also know that the standard pressure at sea level is 2992 inches of mercury, or 1013.2 hectopascals, and the standard temperature is 59 degrees Fahrenheit, or 15 degrees Celsius. As I said before, the equator gets a lot more sunlight, and that's where all the warm air is. Now warm air rises, and as it does, it starts flowing towards the poles where it gets cold, sinks back down, and flows back along the surface, back to the equator. Now if the Earth stood still, that would be a perfect model. But we don't stand still, we're rotating constantly. At the equator, our Earth is spinning at about 1,000 miles per hour, while at the North Pole, it's way less than a mile. That speed change is what's behind the Coriolis effect. If we take an air mass at the equator, it starts out with that 1,000 mile to the east velocity. As it flows north, the Earth underneath it slows down, and it looks like the air mass is going to the right. If you take an air mass from the north, it starts with almost no velocity, and as it flows south, the earth underneath it speeds up, and the air mass takes a right-hand turn again. Because of this deflection, the air actually gets deflected so much that it breaks up at about 30 degrees latitude, 60 degrees, and 90 degrees. And so we have 3 different cells instead of one giant cell. From the equator, that warm air rises, it flows north towards 30 degrees latitude, and it sinks back down and flows back to the equator. As it flows back, it gets turned to the right, and we call that the Coriolis effect. Also, as that cold, dense air sinks at 30 degrees north, it starts flowing up along the surface as well, up until 60 degrees latitude. And as it flows north, it gets turned to the right, and you have westerly winds in the United States. So generally in the United States, whatever is west of you in terms of weather will be where you are in just a couple days. Now on a small scale, we can't see the Coriolis effect, but one fun way to demonstrate it is if you and a friend get on a merry-go-round, you know, one of those unsafe playground equipment things that probably don't exist anymore, and you stand opposite of each other, and one of you has a ball. As it rotates, you can throw the ball to your friend right across from you, and chances are it won't get to them, because as your friend moves away from where you threw the ball, it will look like everything curved to the right. Now let's talk about pressures. There's low and high pressures, and you can think about high pressure as being a hill, and a low pressure as being a valley. And in fact, that's what it actually is. The reason there's high pressure is because there's more air on top of that spot, which means it's heavier. And then a low pressure is where there's less air above you in the atmosphere, so that's a lower pressure. Now air flows from a hill into a valley, or from a high pressure to a low pressure. As air flows towards a low pressure, of course it gets turned to the right by the Coriolis effect. So what actually happens is it doesn't quite get to the middle of the low pressure, but it ends up circling counterclockwise around the low pressure. Low pressures suck air in, and if it's moist, it gets lifted up, and it becomes clouds, rain, and generally unfavorable weather. High pressures, on the other hand, usually have good weather because it's cold, dense, descending air, and it's usually dry. So high pressures have descending cold air, and it flows out from the high pressure, and as it does, once again, Coriolis effect takes over, and it rotates everything to the right, and so you have a clockwise rotation around the high, and a left counterclockwise rotation around the low. And the way I remember it is left for low. Something to kind of think about is if you're planning a flight and the weather is generally good around where you're trying to fly, and you can take advantage of the tailwind, knowing which way the pressure is rotating. On the right, you have a wind flow chart. It's an art project that somebody did. And you can see that around the Texas area, there's a high pressure that rotates to the right, clockwise. And around the Columbus area, there's a counterclockwise rotation around the low. You might know that water heats up slower than land. So when you have land and water right next to it, the air over the land gets heated up more, and it rises. Then it flows up to the sea, gets colder, sinks back down, and it flows along the surface back to land. And that's what we call a sea breeze. Kind of stinks when you just get out of the water and it gets all cold and breezy, but at least now you know why. At nighttime, the cycle reverses. The water is still warm, but the land cools off a lot quicker, so now you have warmer air rising over the water. It flows towards the land, gets heavy and cold, and sinks down, and flows back out towards the water. So if you're on a boat next to the shore, you'll get what's called a land breeze. Because of uneven heating, things like land and water and forests and fields, they all heat at different rates, and especially closer to the ground when you're flying, maybe when you're landing, you'll see all these air pockets, or rather you'll feel them as a little bit of turbulence coming into land. Something else to keep in mind as you're coming into land, especially if the winds are a little bit strong, is that there's mechanical turbulence. All the hangars, all the buildings, the fuel pumps, all this stuff around the airport, all those things disturb the airflow patterns, and they can create a little bit of turbulence. In mountainous areas, you also have updrafts on one side of the mountain and downdrafts on the other side. And usually wind blows a lot faster at higher altitudes, so it's a lot more dangerous if you're flying in mountainous areas, especially on the downwind side. A wind shear is a change of wind speed and or direction over a small area. As you can probably guess, wind doesn't all flow in the same direction. Around different pressures, different altitudes, the wind changes, and if it happens to change over a small area, where that change happens from, let's say, a south wind to a west wind, there's going to be a little bit of turbulence, and the air will be a little bit rough. Now, usually, this is associated with a frontal system, a thunderstorm, or strong upper-level winds, but it can really happen at any altitude, any time, and sometimes it's even due to mechanical turbulence closer to the ground. Wind shear is fairly dangerous when you're close to the ground. The reason it's so dangerous is not because of turbulence, it's because of rapidly changing performance. So wind shear by definition is a change of wind speed and or direction. So imagine you're flying along and you're on final and you have a headwind of 20 knots. Everything's going great, you have that 20 knot headwind, but then all of a sudden it changes to a 20 knot tailwind. Now 20 knots might not seem like a lot, but you just lost 40 knots. And if your approach speed is 60, now you're at 20 knots. Now wind shear can happen at any altitude. Usually at higher altitudes, it's just turbulence. Now the worst type of wind shear is a microburst. You can get up to a 6,000 foot per minute downdraft. That's a lot. You can also lose about 90 knots of speed from headwind to a tailwind. There's a lot of turbulence and wind shift, and of course there's performance issues. Let's say that you were taking off in this example and you encountered a microburst. At position 1 over here, you'd have great performance. You'd have a lot of headwind, the airplane would be climbing really well. At position 2, you'd have decreasing headwind, and you'd start getting pushed down towards the ground. As you get to position 3 and 4, you have an increasing tailwind, and you don't have as much performance anymore, and this picture might not even be accurate. You might be in contact with the ground already. So avoid microbursts if you can. I definitely read more about them in the P-hack. So anytime you hear wind shear from ATC or from an ATIS or an AWAS, just be cautious that a microburst can happen, especially if you're close to an area of weather like thunderstorms and frontal systems. So let's shift gears a little bit and talk about isobars. Isobars are lines that connect areas of equal pressure to one another on weather charts. And if you see closely spaced isobars, that means that the pressure changes rapidly over a short area, and there's a pretty good probability of wind shear. Something else on weather charts that you can look at are these wind barbs, and they're basically a circle that represents the station, and then little lines that represent how much wind there is. Every long line is 10 knots, and a smaller line is 5 knots. So for example, at this bottom left here, we have 3 big lines and a short line, and that's 35 knots. And where that line is positioned tells you where the wind is coming from. So the wind is coming from the right going to the station, so it's coming from the east at 35 knots. And then if you see a triangle, like the next one here, that's 50 knots coming from the north. And the one after that, it's a mixture of triangles and lines, and that happens to be 105 knots from the west. Stability is the atmosphere's resistance to vertical motion. As we know already, warm air rises, it cools and expands, and then colder air replaces that by sinking and getting heavier and getting denser. Now, cool, dry air is very stable. It doesn't have a lot of instability, it doesn't want to move up and down, it's just kind of hanging out and being chill. Now, moist, warm air is unstable. When you have water vapor in the atmosphere, the air is a lot less dense. And that's why performance gets decreased when there's humidity, because less dense air is a less happy airplane. There's always some amount of water in the atmosphere. How much depends on the temperature. For example, for every 20 degrees of Fahrenheit increase in temperature, the amount of water that the atmosphere can hold is doubled. Humidity is the amount of water vapor in the air at any time. Now, relative humidity is the percentage of how much water the air has versus how much water the air can hold at that temperature. If you've seen a METAR, you've seen that there's a temperature and a dew point in that report, but why do we care about the dew point? The dew point is the temperature where the air can't hold any more water. In other words, it's 100% full of water and it can't hold any more. Now, when the temperature of the air gets reduced to the dew point, the air is completely saturated and the moisture starts to condense out of the air. And that's how you get fog, frost, clouds, rain, snow, etc. So we do care about the dew point, and especially the temperature dew point spread. When they get within a couple degrees of each other, you know that there's a really good chance of fog or low clouds or bad visibility and things like that. As moist, saturated air rises, the temperature and dew point converge at about 4.4 degrees Fahrenheit or 2.5 Celsius. And so what this means is you can figure out the height of the base layer of clouds. So if you take your temperature, subtract the dew point, and divide it by 2.5 degrees Celsius, you can multiply that by 1,000 feet, and you can get your cloud height in feet AGL. Okay, so we know that when temperature and dew point get close, fog, clouds, precipitation forms, There are a couple of ways to get air cooled down to that dew point. One of those ways is a warm air mass moves over a cold surface, and the temperature decreases down to the dew point. Another way for that to happen is you get cold and warm air and they mix in the middle, and the general temperature decreases. At night, air cools through contact with the cooling ground, and finally, if air rises or gets forced up, that's how it also can cool. So at night, you probably know that you have dew on the ground, little droplets of water. Sometimes you get frost, and the reason that happens is because at night, the ground cools off a lot quicker than the air, and when the warm air comes in contact with the ground, it cools down to the dew point, it gets to 100% relative humidity, and condenses out of the atmosphere as water droplets. And if the ground is below freezing, those water droplets become frost. So I hope that was at least a little bit interesting and informing. There's no way I can make this weather thing into a one video. That would just bore people to death, and my voice would probably give out. So come back for part 2 of weather. Until then, have fun, fly safe, always keep learning. See you next time.
Which we will. Any questions right off the bat? I'm gonna cover a bunch of it. First term, ATC, air traffic control, he said that a couple times. So, then isobars used to be a really important part of flight planning, not so much anymore. An isobar is a line that connects common pressure setting. You know, he showed that, and we used to see it on the TV, meteorology. You know what I mean? When the isobars are close, you're gonna have more wind, air trying to go from the high to the low. So if you have a lot of distance between your isobars, those lines of continuous pressure, so the further they are apart, the less chance for wind. So it's a flight planning thing for you. If you see that there's a high close to the low, and how high is the high and how low is the low, you see those isobars. And you can also use it for, you know, maybe altering your route because of a tailwind. You take advantage of a tailwind. Maybe, you know, but low pressure up over Oregon can affect the wind down here. It can be a lot of miles away. That's important to know. So we'll look for isobars. Again, that used to be a flight planning thing that we looked at a lot. Now we have a little more modern presentations and just shows little wind arrows. You know, and you'll see that they're kind of moving on the bigger map, but you're trying to just plan if you can to utilize the tail map. Coriolis effect, anybody else know examples of what that is? Coriolis, you ever heard of that?
Direction of the wind from the equator,
Yes.
always moves to the right.
Well, from below, but yeah, up in the northern hemisphere, the low goes left, correct?
That, okay, but that's when we get above what, 30,
Well, at the equator, it actually goes, it splits right there.
okay, I don't know.
Okay. Well, the most common example is we see a toilet flush. When you flush a toilet, the water goes like this. Because it's low, all of a sudden you've gotten rid of the pressure is down below. And in the southern hemisphere, if you flush your toilet, the water goes to the right.
No.
Yeah. A little trivia. I thought somebody might have heard that. I was gonna say you're a plumber.
Yes, I am a plumber, yeah.
Okay. So mountain flying, I was gonna say isobars really matter. Wind shear is gonna be associated with a microburst. You know, you're gonna be in thunderstorm country. So don't over freak out necessarily about that around here. You would know if you're in that kind of scenario. So METARs you talked about, which is the coded and or uncoded string of letters that kind of glossed over that. We're gonna get into that next coming up. Any other question?
Does
Yes.
wind change at different elevations, like doesn't it change directions?
It does. And that's a kind of another lesser known term. There's a thing called surface friction. In other words, when the wind is going a certain way here, as it goes up, it's gonna change. And Coriolis also. In other words, as you go up in time, it's. Yeah, an important thing you need to talk about was we call it lapse rate. In other words, the temperature gets cooler by 2 degrees Celsius or 3.5 degrees Fahrenheit per 1,000 feet. So at 10,000 feet, it's basically 35 degrees cooler than here. Not always. And-
2 degrees per thousand?
Yeah, 2 degrees Celsius, or 3.5 Fahrenheit about. So that's how we come up with that term inversion. You know, our valley fog that we all kind of grew up around here, you know, the Central Valley, is cold on the ground on a winter night. And then as you go up, it gets warmer, and that keeps that fog down. It won't dissipate or evaporate.
Mm-hmm.
And it's warmer. And that can affect your flight planning. You know, that's called an inversion. So the temperature isn't getting colder, it's getting warmer. And it sometimes in the fall, why the smoke will disappear and sometimes it won't, it lays in. That's also pressure related. You know, there's a high pressure air, the air is heavier. You talked about that column of air having weight.
Mm-hmm.
If it's a high pressure, and so we kind of glossed over that, we use this thing called inches of mercury, an altimeter. And there's a little knob, and when you hear the weather, they'll say the altimeter setting is 2992 inches of mercury. It doesn't say that. You just dial your inches of mercury on the altimeter, and that way it tells you how high you are on the ground, because you don't. Well, I mean, we do know what our field elevation is, but we don't once we're in the air, and we want to be on the same standards as other airplanes, so that we're comparing apples to apples on altitude. I was going somewhere with the inches of mercury. Anyway, you'll hear that a lot in our, it's also called an altimeter. Altimeter setting is in inches of mercury. In Europe, they use millibars. And that's the last you ever need to hear the word millibars. Okay. All right, can you make the next one?
Yep.
Glare. Is that kind of okay?
When we left off, we were talking about cooling air masses, and this leads perfectly into fog. Let's clarify a few things before talking about fog. Radiation is energy transferred by radiating from the surface. So for example, if you have your stove on and you put your hand above it, that's radiation. The stove is radiating heat and you can feel it. And then there's conduction. If you touch the stove, heat is being transferred directly to you through direct contact. So that's conduction. And then convection is when molecules transfer energy. So if you have boiling water in a pot, the hot water molecules from the bottom of the pot rise up and then they sink back down as they cool and then rise and cool and rise and cool. And that's convection. Okay, so now fog. Radiation fog happens on clear, calm nights with little or no wind. The air stays warm, but the ground cools off rapidly, and it radiates that cold, and it brings the air down to its dew point, which causes fog. Now, radiation fog happens with no wind, and if there's any wind, that will dissipate the fog. Also, when the sun rises, it will warm up the temperature, and that can hold a lot more water, a lot more moisture, and that will burn off the fog. Something else that's related to this is your shower mirror. You probably know that as you take a shower, the mirror fogs up, and the warm, moist air, when it gets to the mirror, it condenses and forms water droplets. One fun way to clear up your mirror is actually to take a hairdryer and blow some hot air on those water droplets. And as we talked about earlier, when you heat up the air, it can hold a lot more water. So when you get the hairdryer going, that's hot air, and it can hold a lot more water, and so your steam will disappear off of your mirror. Advection fog happens when you take a warm, moist air mass and you move it over a cold surface. Advection means moving. So when you get winds up to 15 knots, that'll allow that fog to form and actually intensify. And you've probably seen this if you live on the coast somewhere, like in San Francisco. You get warm, moist air that comes in from the ocean, and as it moves over cold land, it'll get cold, and you get advection fog. If you live in the mountains, you probably know about upslope fog. If you take moist, stable air and you force it up a sloping terrain, air cools and it reaches a dew point, and then you get fog. You also need wind for this fog to form, and it can last quite a bit actually, and it doesn't burn off when the sun comes up. I think the most awesome type of fog is steam fog. You take cold, dry air and you move it over warm water. The water will evaporate, it'll rise, and it will condense and resemble smoke. So you can see this either early in the morning or kind of late at night on the lake. When it's super cold, water can actually go from water into ice crystals and cause ice fog. It looks really cool, but if you fly through it, it's really dangerous because you become an ice particle immediately. For any visible moisture to form, like clouds, air has to reach its saturation point, or 100% relative humidity. And that's where that relative humidity term comes in. You also need some sort of particles for water to condense onto to make a water droplet. Those little particles are called condensation nuclei. The condensation nuclei can be smoke particles or tiny dust particles or salt. So like over the ocean, there's a lot of salt evaporating, so water droplets can form on the salt. If there aren't any of these particles for water to form, water can actually cool down to below freezing and not freeze because it has nothing to condense onto. If you happen to fly through some of this super cooled water, your airplane becomes a condensation nuclei and you freeze up immediately because that cold, super cold water is still water, but it's super cold, it's below freezing, and it can freeze on your airplane. Super dangerous stuff. And just as a little note, if there's any visible moisture and the temperature is below freezing, you can expect to see ice. In other words, if there's fog or clouds and it's below 0 Celsius, you can expect to have ice inside the clouds. We have a couple cloud types. They're low, middle, high, or clouds with vertical development. Low clouds are usually below 6,000 feet, middle clouds are from 6 to 20,000, and then high clouds are above 20,000. And then clouds with vertical development are usually cumulus clouds that build into a towering cumulus or cumulonimbus, and they build into thunderstorms because of convection, or the up and down motion of moist, warm, unstable air. Cumulonimbus clouds have a lot of moisture and a lot of unstable air, and they usually have things like hail, thunderstorms, lightning, wind shear, and they're the most dangerous cloud. That's why on your METAR or your ATIS, you'll see CB or cumulonimbus, because that's something you want to avoid. Just as a fun little fact, the up and down drafts inside a cumulonimbus cloud can exceed 3,000 feet per minute, which, as you know, is really fast. When you think of clouds, you probably think of cumulus clouds. Those are those puffy clouds that look like somebody took a bunch of cotton balls and just stacked them together. Those are cumulus clouds. There's also stratus clouds, and they're formed in layers, they're flat. And cirrus clouds are up high, they kind of look like stretched out cotton candy, they're nice and wispy. And anytime you see a nimbus in the cloud name, like cumulonimbus or nimbostratus or something like that, nimbus means rain, so that's a rain cloud. The most awesome looking of them all is a lenticular cloud. It happens over mountains when there's wind and when there's moist air. As the air gets forced over the mountain, it creates mountain waves, and as it goes up and down, at the top of that wave, you get lenticular clouds. As the air cools and reaches a saturation point, it forms like a lens-looking cloud, and it looks really awesome. But what it means is there's a lot of turbulence and a lot of strong winds and up and down drafts. On the METARs, I'm sure you've seen scattered clouds, few clouds, overcast clouds. What does that actually mean? If you take the sky above you and you divide it into 8 equal pie sections, when you have 1 to 2 sections covered with clouds, that's called few. 3 to 4/8 is scattered. Broken is 5 to 7/8, and then overcast is the entire sky above you is covered. Now a ceiling is the lowest layer of broken or overcast clouds. So for example, if you have scattered at 1,500, few at 2,000, broken at 3,500, and scattered at 5,000, what's the ceiling? A ceiling can also be vertical visibility up into fog or into haze. Because you can't determine what the ceiling is, it's not broken or overcast, it's fog. How far up you can see it can be considered as ceiling. And on the METAR, you'll see that as VV, or vertical visibility, of however many feet. We get precipitation because water or ice particles in the cloud grow until the atmosphere can't support them anymore. They get too heavy and then fall down to the ground as rain or snow or ice. Something cool that can happen is called virga, and this is rain that falls, but it evaporates before it gets to the ground. And so you have these cool-looking streaks coming down from the cloud, but never actually getting to the ground. Now let's kind of zoom out from a cloud perspective and look at bigger air mass picture. Air masses originate in different regions, and where they form, that gives them their characteristics, like temperature and moisture and dryness and things like that. And so if you have an Arctic air mass that forms over the polar region somewhere, usually it'll be cool and dry. But if you have a Pacific maritime air mass, for example, that will be warm, moist air that forms over the water. Moist, unstable air causes cumulus clouds, it causes showers, and it causes turbulence. If you take an air mass and move it over a colder surface, that doesn't cause convection, but that air mass becomes stable, and usually that means poor surface visibility. And that's because smoke and dust and other particles, they can't rise up and down and they get trapped close to the ground. Stable air masses produce low stratus clouds and fog. So you can tell that a stratus cloud usually means stable air and almost no turbulence, but cumulus clouds means unstable air and a lot of turbulence with ups and downs. When air masses run into other air masses that are different, they form a front, or a boundary layer between the two. When there's a front, the weather is always different on the other side of the front, and that's because it's a different air mass with different properties. We have a warm front, a cold front, a stationary, and an occluded front. And the front gets named based on the air that's coming in to replace the air that's currently there. For example, a warm front means that warmer air is coming. One important thing to point out, warm and cold don't refer to temperatures. Everything in weather is relative. So a warm front can be minus 20 degrees if it's replacing something that's minus 30 degrees. In a warm front, warm air advances and it replaces the colder air that's there. Warm fronts are typically slow moving at about 10 to 25 miles an hour. As the warm air comes in, it goes on top of the cold air that's there, and it creates a nice little slope, slides over that cold air, and eventually it pushes it out of the area. If you have warm air that has a lot of moisture and a lot of humidity, as it gets lifted on top of that cold air, the temperature drops, you get condensation, and you get precipitation. You can tell a warm front is coming if you look outside and you see cirrus or stratus clouds, and sometimes you even get fog. As the front approaches, you'll see stratus clouds, maybe possible drizzle or some rain. The visibility is typically poor, but as that front passes, it'll get better. After the front passes, you'll have stratus clouds, you'll have rain showers possible. Your visibility will improve, but it might be hazy for a little bit after that front passes. Now, one front is fairly slow, so it might take a little while for that front to pass through. We have a nice little example in the PHAC. In this example, you're flying towards a warm front. What you see in Pittsburgh is a high layer of scattered cirrus clouds at 15,000 feet. As you get to Columbus, you'll see lower clouds with more layered stratus clouds at a ceiling of about 6,000 feet or so. Visibility decreases to about 6 miles. Around Indianapolis, the weather deteriorates to broken at 2,000 feet and 3 miles visibility with rain. Past Indianapolis, the ceiling visibility is IFR, and if you were to get stuck in Indianapolis, it'd probably take a few days for that front to move and for the weather to improve. The cold front is kind of like a mean playground bully. It's cold and it's dense, it's stable, and it moves really fast, 25 to 30 miles an hour or so. It's kind of like a snowplow, and it runs into the air at high speed, and it forces it up really quickly. And that rapidly ascending air cools quick, and it forms clouds. With a cold front, prior to passage, you'll see cirrus or towering cumulus clouds, or even cumulonimbus clouds. You'll most likely have rain in the area. As it passes, you'll have towering cumulus or cumulonimbus clouds, and you will have heavy rain, lightning, thunder, hail, and that's because the cold air is shoving everything up and out of its way. You have a lot of updraft, a lot of up motion in the air, and all that air cools. It becomes rain, it becomes hail, it becomes all those things. And then you also have strong downdrafts as all that stuff comes back down to the ground. With a cold front, you can also expect poor visibility with all the precipitation, and also gusty variable winds. Also, as the cold front passes, your temperature will drop because it is, after all, a cold front, and the pressure will fall rapidly. After the front passes, the clouds will dissipate into small little cumulus clouds, precipitation will start going away, the visibility will get better, and it'll stay cooler. If you have a fast-moving cold front, it could create a narrow band of weather and what we call squall lines. That's a bunch of thunderstorms all in the same line, and it usually clears up rapidly, but while it's there, it's pretty violent weather. Looking at this example, if you're departing Pittsburgh, you'd see scattered clouds at about 3,500, 3 miles visibility, and maybe a little bit of haze or smoke. Around Columbus, you'd see clouds with vertical development and broken clouds at about 2,500 feet with 6 miles visibility with a falling pressure. At Indianapolis, it would be overcast at 1,000, 3 miles visibility, thunderstorms, and heavy rain showers. By the time you got to St. Louis, the weather would be a lot better with scattered clouds at 1,000 and 10-mile visibility. So as a quick summary, cold fronts are fast and they bring violent weather. Warm fronts are slow, they bring low ceiling, poor visibilities, and rain. Cold fronts bring storm and gusty winds and turbulence, but they pass very quickly. Whereas warm fronts stick around, so you'll get the rain, the fog, the drizzle for maybe a couple days as it moves out of the area. Something to keep in mind and maybe look for, when you fly across a front or when a front passes, the weather will change. Things like temperature, moisture, stability, but most noticeably, the wind speed and the wind direction will change. A stationary front happens when you have a cold air mass and a warm air mass, and they have relatively the same force. One's not trying to shove the other one, and so they stay in the same area. And you usually have a mixture of both cold and warm front weather, and it kind of lingers for a while. An occluded front happens when you have a fast-moving cold front that catches up to a slow-moving warm front. There are two types of occluded fronts. In the first type, you have cold air in front of warm air, and then the coldest air catches up to all three of them. So it pushes the warm air aloft on top of the cold air, and it pushes the cold front ahead of it. Now the other type is cold air, warm air, and then cool air. So it's not as cold as the stuff in front of the warm air, but it's cooler than the warm air that's in the middle. So what happens is that cool air forces the warm air up, and itself it rides up on top of the cold air, so you have a lot of up motion going on. If the air is unstable, that will produce a lot of severe weather, like embedded thunderstorms, rain. I'm sure by now you're wondering how thunderstorms work. Thunderstorms have three different stages that make up the life cycle of a thunderstorm. We begin with the cumulus stage, and this is where unstable and moist air begins to rise up and increase the vertical height of that cloud. You have strong updrafts that prevent moisture from falling. So in the cumulus stage, you have mostly updrafts. When you get to the mature stage, that happens within about 15 minutes or so, the water drops get too heavy for the updrafts and they start falling down as rain or hail. And this is the most violent period in a thunderstorm, is this mature stage. That's because you still have updrafts, but you also have downdrafts. Warm air is rising and cold, moist air is falling. So there's lots of turbulence in and around the clouds. Once the motion at the top of the cloud slows down, when the updrafts kind of slow down, the top will spread out and it will make an anvil shape. You can tell which way the storm is moving by looking at the anvil top, because the upper atmosphere winds will blow it in the direction that the wind is blowing. Finally, we get into the dissipating stage, and this is where downdrafts spread out and replace all the updrafts, and the storm can't sustain itself anymore. Some of the things that can happen in a thunderstorm, obviously turbulence, and you can get that all the way up to about 20 miles away or so. You can also have a gust front when the mature stage starts, when you have the downdrafts. Obviously, you can have wind shear, and then when the thunderstorm starts dissipating, you can get those microbursts that we talked about that are super unhealthy and bad. Don't fly through them. There's a really good chance for icing. There's a lot of moisture in the air, and the water can reach a freezing level really quickly, and you can even get super cold water droplets that make your aircraft become that condensation nuclei I mentioned earlier. A good rule of thumb, once again, is anything below 0 degrees with visible moisture, there's a potential for icing. Some notes about thunderstorms: don't try to fly over them. They can go as high as 50, 60,000 feet. If you ever have to fly around the thunderstorm, stay at least 20 miles away. At least. I'd go a little bit more. Some of the turbulence and hail can get tossed way outside of the clouds, and you can get turbulence thousands of feet above the thunderstorm as well. Just because you're not in a cloud doesn't mean the air isn't moving. I mentioned a squall line earlier, and a squall line is a band or a line of thunderstorms. Sometimes it can be long, it's usually narrow, but it can be long, and you might not be able to go around it, and usually it's associated with a fast-moving cold front. Some people wonder what happens if you get hit by lightning. Usually nothing happens, because an airplane is built like a Faraday cage, and if you know anything about that, basically if there's any sort of energy input on the Faraday cage, it will flow through the entire structure of the airplane, and it will flow out to the static wicks at the tail or on the wings. So that's why you pre-flight those and make sure they're on the airplane before you go flying.
But you'll know it.
But the worst thing that lightning can do is probably blind you. And you might not know, but an average jet airplane gets hit about once a year by lightning. So that's basically it for weather. I know there's a lot more information, and weather theory is constantly evolving. So look it up yourself if you want to know more. And until next time, have fun, fly safe, and always keep learning. See you next time.
Keyboard.
The term icing, in flight training environment, don't let that scare you too much, because again, it's part of what we're talking about. We don't fly into the clouds. That's another level of aviation. So you're not really going to get icing. But in lots of parts of the country, not so much here, you can get rain up above that's so cold, and your airplane is cold, that when it rains onto you, it does ice up. But that's pretty rare. Yeah.
Radical ice particles in that sort of.
Yes.
What do you call those, that strutter tubers stuff?
Well, you know, see, there's a couple layers. See, there's the repetitive stratus, and then there's another layer above that. If you're up high, you'd be in between there. But there are a little bit of alto cumulus way out there. See the more puffy ones way out there, and then it would look to me like a stratus layer below that. It's a pretty interesting combination right there. It's a little more puffy out that way. You know, that real round, or not round, but you know, real puffy we're talking about. And when do we see that? Going back to the fronts, when do we see all those puffy white clouds on a clear, good visibility day? What just happened when we see those? What kind of front? A cold front. Cold front just happened. You know, when it rains, and then the next day we see that, and it's nice and clear. So that was cold front. And there's no number. How cold is it? It's colder than it was. So, but yeah, I'm not. I don't know.
When you have those test clouds, the cold front there, is there a chance of the squall line?
Well, squall line is thunderstorms. They would be cumulonimbus, like a bunch of them.
And do not more graduated.
They would be, there's no minimum altitude or maximum altitude, but in other words, they would show up as not just an isolated thunderstorm. What's a little scary, sometimes a thunderstorm is embedded in clouds that otherwise are pretty benign, but you just can't see it with your eyeball. There could be a thunderstorm there that you can't see. So we count on other weather information for thunderstorms.
Can you have a thunderstorm without a cumulonimbus?
Not really.
And
Yeah, not really.
so that-
You
that'd
can
be
have
up
lightning.
60,000 feet.
You can have lightning, which is a thunderstorm, not necessarily from a cumulus cloud. You can get it from, you know, actually across the southwest where it's dry, and a lot of times there's no moisture that we need for a cumulonimbus cloud for the conventional thunderstorm. But you'll get out of just a straightest cloud, you'll get lightning. It's almost more like staticky, you know, kind of a stuff. It's dry, and you can create lightning where there's no moisture comes out. People in New Mexico know that. They'll see thunder and, you know, I mean lightning, and hear it make a big thunderstorm, and there was no rain came out of it. Fantastic.
Those are friction, right, in the clouds.
Friction,
Yep.
you mean what causes the lightning?
Yeah.
I just did that analogy, but I'm not sure that it's really friction. It's a positive and negative charged,
Right.
you know, contents, and, you know, what is lightning? Electrician, what's electricity? I don't know. Does it move through a wire or does it touch? I don't know. Let's see, something else I was gonna hit was, anyway, okay. Any other questions though?
You said it, you know when it hits you in the front.
Yeah. You're not likely to get hit by lightning if you're flying VFR. In other words, if you're not in the clouds, it just doesn't come out of nowhere. You kind of know you're in it. But it doesn't take down airplanes, but I mean, it rocks them. I mean, like I said, you'll know you were hit. You know, if you're in an airliner as a passenger, there's no doubt. I mean, if it was hit, everybody, it makes a lot of noise, the whole, well, kind of big deal lights up. Anyway, next, can you hit the go?
Arrow.
There it goes.
Hey guys, John from FlyMikeAlpha.com, and today we are going to talk about METARs and TAFs. And you might notice this is part 1 of 2. In this video, we are not going to get too in-depth into all those crazy weird symbols and remarks you hear about sometimes and you see in the text. We're going to get into the very basics at a student pilot level of where you should be able to read METARs and read TAFs and understand what they mean at the basic level. And then part 2, we'll dive into all those crazy weird remarks about rain beginning here and ending there, and Virga and snowstorms and sandstorms and all that. So, very basics today. We'll jump right into it.
Key number tower, right, turn northbound approved, runway 24 clear for takeoff.
So we're going to start off with METARs, and we're going to start off with one from the Punta Gorda Airport, KPGD. And we can see here that it was issued the 4th, that's the day, the first number there, at 18:53 Zulu, 14:53 local, and the winds were 120 degrees at 9 knots, 9 statute miles visibility with light rain, that's the minus RA, scattered clouds at 600 feet, broken clouds at 4,800, and overcast clouds or an overcast ceiling at 11,000 feet. Then after that we can see 21 over 19, that means the temperature was 21 degrees Celsius. Dew point was 19, that's dangerously close. Anytime there are 3 degrees or closer apart, we have to worry about fog or mist and low visibility. And the altimeter A2981 means altimeter 29.81. And we're going to stop there. We don't have to worry about the remarks. So those are the weather conditions that were observed at 1853 Zulu. Now, it's anybody's guess what's going on right now. Weather does change, so you may want to wait for the next one to be issued. They are issued typically every hour or after a sudden change in weather, so they should be reissued. Sometimes you'll notice after the time and date stamp, auto, A-U-T-O, and that can mean that all this information is generated automatically at an unmanned weather observation station. Not that it's any less reliable or a METAR without auto is any more reliable. Humans certainly still do make mistakes, but typically there's some human intervention or some human overseeing what the weather station's saying if it's missing that auto designation. Instead of auto, you may also see COR, that would mean corrected. Perhaps that an automated station generated bad information and said the winds were 90 knots instead of 09 knots, and it was corrected by a person. And they won't show you what the correction was, it'll just say COR after the timestamp for corrected. Now let's talk about a couple things that pertain to our wind indication there. So let's say that instead of seeing 120 at 9 knots, we saw the letters VRB. Those would stand for variable, and typically you'll see that when the wind speed is less than 6 knots. And so they simply tell you, hey, the wind's pretty light and it's probably variable from different directions. We don't really know exactly what direction it's coming from. It's light and variable. And so that's what the VRB would stand for. Now, if you saw a wind direction like 120 and then 09 with a G, and maybe after the G you saw 21, that would stand for winds are 120 degrees at 9 knots, gusting to 21 knots. And so that's actually a pretty big difference, 9 knots and 21, but that can happen. And so that's what the G stands for, when you might have winds 12 knots gusting to 18 or something along those lines. It would be displayed as this. All right, now let's go ahead and talk about TAFs. And TAFs are slightly more complicated, same basic layout, however there's slightly more information there. So, a few other key points to know about TAFs before we get into them. They're good for a 5 statute mile radius around the airport. It's a terminal aerodrome forecast, just for the terminal area. If you're going more than 5 miles from the airport, you need to check out your FA, your area forecast. Also, TAFs are typically good for 24 or 30 hours, depending on what airport they were issued at. Most airports around the country are 24 hours. Some of the big international airports are now valid 30 hours out. So for this TAF, for the Punta Gorda Airport, KPGD, issued on the 4th at 1744 Zulu, 1344 local. It's valid from the 4th at 1800 Zulu until the 5th at 1800 Zulu, so good for 24 hours. The winds we can expect initially to be 220 degrees at 6 knots, 6 statute miles visibility with light rain. In the vicinity, we expect to see some thunder showers, watch out for those. Scattered clouds 800 feet, and those are cumulonimbus clouds, so be very careful. There's thunderstorms on the area, CB, cumulonimbus. Broken clouds 2,500, overcast 6,000. Temporarily on the 4th from 1800 Zulu until the 4th at 2000 Zulu, the visibility will be 3 statute miles, rain showers, broken 800 feet. Now this temporary, that means at least half the time or so, or about less than half the time, we're going to temporarily see these conditions. Between those 2-hour time frame, about half of it will be these conditions. That's what the tempo means. Thereafter, from the 4th at 2100 Zulu time, winds will be 240 degrees at 9 knots, plus 6 statute miles visibility. In the vicinity, there will be some rain showers. Scattered clouds at 1,000 feet, broken 2,500, overcast 6,000. From the 5th at midnight Zulu, or 8 p.m. local, we'll have wind 270 degrees at 8 knots, plus 6 statute miles visibility, scattered clouds 2,500 feet, broken 6,000 feet. Starting at 3 a.m. Zulu, or 11 p.m. local on the 5th, we'll have winds 300 at 10 knots, plus 6 statute miles visibility, scattered clouds 2,500, broken 6,000. From the 5th, at 6 a.m. Zulu, 0600 hours, or 2 a.m. local, we'll have wind 320 at 8 knots, plus 6 statute miles visibility, few clouds 2,500, scattered clouds 6,000 feet still. From the 5th, at 1400 Zulu, or 10 a.m. local, we'll have winds 340 at 12 knots, plus 6 statute miles visibility, and scattered clouds at 6,000 feet.
Hey guys, thanks for watching part 1. If you decide you want to learn a little bit more about meters and tasks, check out part 2 down below. Any questions at all, leave them in the comments below. Make sure you give us a thumbs up and subscribe to our YouTube channel over on the side there. Also check out our Patreon page, how we fund all our videos. Thanks so much for all your support. Thanks for watching. We hope you get to fly every day. And if you...
Oh, I thought you did. Okay. The timestamp. The first is the day. He was using the 4th of the month. No, any question about that? The timestamp. And then the Zulu. For you guys, Zulu means from here, that's a universal coordinated time. It's a place in England, basically, the zero longitude of the planet is where the clock starts, if you will. So we are 7 hours later here. So if you saw Zulu time, that's 7 hours later than here. You know what I mean? In other words, so if it was 10 a.m. here, it's 1700 there, which is the same as 5 o'clock. Okay, so it's 7 hours later there. The planet rotates that way. Do you follow me?
So you subtract 7 for us?
You subtract, yes. In other words, it's later there, yes. Or add from here to get to there.
And
yes.
why do Zulu?
Well, the reason for the Zulu was because everybody around the planet can look at the same weather forecast at the same time. Not everybody's in our time zone.
Right.
You know, when we get into these maps, it's for people everywhere. So we don't always know what time zone we're in when you're flying an airplane. You don't know time zone. And of course, we have our cell phone. It corrects pretty good on that. But if you'll notice in an airliner, your cell phone doesn't even really upgrade. You know, you can, if you kind of know where you are, it didn't really update. But that's so we're all on the same page for the time stamp. Then the other thing we're a little light on is the identifier. Don't be confused by that. Most airports in the United States start with a K. So like LAX would be KLAX, and that's the international designator. So we know it as LAX, be KLAX, and here they had K before every airport. Smaller airports like here, we're Oscar 22. We're not K Oscar 22, but Sacramento, KSMF. So you see K a lot before the 3 letters. So there could be a 3-letter. And then Europe is like an E first, and the Pacific, Hawaii, and out there is a P first, but we're all Ks. He hit on the temp and dew point spread that comes up in there. And that's an important key for us to know that the temp and dew point spread, like on a winter morning, when it's clear here, but foggy down in the valley, we look at temperature and dew point spread. If they are close, and the temperature's getting colder, like at night, if it looks, well, another part of your flight planning is, if you think that temperature and dew point are gonna get close together, when they get to 0 gap, you're gonna have rain or fog. You're gonna have a lot of moisture in the air. So in your flight planning, you wanna know that. That's a crucial part of your.
Does that tell you what elevation that you're gonna have that dew point at?
Well, this is, in other words, you're looking at our airport when we a flight plan from A to B. We're looking at our weather, and we're gonna look at the weather we're going to. And maybe a couple airports en route, so we're gonna fly over them. If we're gonna go from here to San Jose, we wanna look at Stockton and Modesto as well. And, you know, and it may tell us in remarks, the temperature forecast. If you're looking at the forecast, it's going to be cooler, and the dew point number is up. You're going, it could fog in there tonight. That could matter to us. Anything else on that,
It is TAF and what else?
yeah, METARS, which stands for,
I don't know the answer, but I know how to look it up.
meteorological, absolutely should know what that is. TAFs is terminal area forecast. So, terminal area forecast is your forecast for the next 24 hours. METARS is the observation of current. This is what it was at that timestamp. It said the 04 at an hour ago, or whatever that timestamp in Zulu time was, an hour ago, here was the weather. And it usually moves every hour, so the METARS is updated but it's called a surface observation. And a surface observation is magnetic because it's about the runway, and the reason versus true is our runways are magnetic. So in other words, runway 17 is 170 on the compass. So the wind we want to know for crosswind and which runway we're going to use. Whereas when we get to altitude, our winds aloft forecast we'll look at later is in true. So we would have to convert that what we were doing on our wind wheel last week. If we want to know what our compass setting is going to be when we're looking at winds aloft, we may have to convert that true, and we'll talk about, we did that last week. What was your other question? That was good. METARS, what is METARS?
One more time.
What it equates to though is current surface observation.
Okay.
The last hour. And, yeah. I just looked it up this afternoon. I I'm supposed to know what that is, but current observation. Okay. Can I get that?
Meteorological aerodrome report.
Okay. Meteorological aerodrome report. Excellent. I like it.
You can use the internet instead of the book.
Yeah.
I still can't find it. It did, was it in the index?
Aerodrome report. Oh, what is it?
I'll go back.
That's it.
That was a lot. We threw a lot at you there, I think. Right? Right, Dave? Okay.
It's tough for a first day.
And like the first guy, that's fire hose night. That was all, there was nothing controversial in there though. But the fronts, they went cold front, warm front, occluded front, that's complicated stuff. Basically, cold air is heavier, we know that. And so when the fronts or masses of air hit each other, the warm is gonna go up and over. So that creates a kind of cloud. And does that matter to you? Well, it kind of doesn't, because the area forecast we rely on, it just tells us basically what kind of, it won't say what kind of clouds. It's going to say expected visibility is 5 miles, and when we're flying from here to San Jose or something, 5 miles, that's not real good. You know, that's not a good day, so it affects our planning. You know, we like to look out and see 100 miles. And so reduced visibility, plus the reason we started with the airspace thing is we better make sure when we fly through some airspace, we don't get to say, well, we didn't know we were over your spot in Modesto, you know? No, you gotta know that. Increasingly, we're relying on our phone to tell us where it was, or some kind of GPS device. But ultimately, the map, you know, that depicts these kinds of airspace, just because you can't see, doesn't mean I didn't know I was over the tower in Fresno. That's this bad answer. Okay, so that's kind of why we introduced airspace and weather, because the weather is going to affect your ability to navigate around that airspace. So you've got to be able to read a METARS and a TAFs and say, should we go fly in there? Maybe we don't want to do that today. Okay, so nobody knows everything about weather, that's for sure. It's a learning kind of thing, but you have to be careful with it. But it deserves constant study. And we're getting more and more decoded. Oh, part of the term, you know, the reason there's these codes that look kind of crazy, somebody brought up that point. You know, near 15, 20 years ago, it was sort of a broadband of teletypes. You know, we kind of grew up with this thing called this teletype. There'd be this machine going chunka, 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 and it didn't have infinite pixels to tell you stuff. You know, they were saving ink on paper, and they condensed it, and it was up to you to learn to uncode this stuff. So you're going, what's with this code? Well, so nowadays, your ForeFlight and all these apps that, what they call decode the thing, and tell you, you're going, well, why did you code it in the first place? That's sort of the throwback answer was, you remember that, remember? The weather machine, chunka chunka making noises. They just didn't have that space, so they tear off a little piece of paper, here, dude, here's your weather. And, you know, nobody ever knew all those codes. Just so many remarks and all, you know, that was still kind of like trivia. And you would go to a book, you know, everybody had their little sheet book over here, acted like we know all that stuff, but you know, you develop your own book of your things, maybe how to pre-flight your airplane and what those light gun signals were. You'll end up with your own little binder of things that you need, because you can't memorize everything, you know what I mean? So you end up with your own extra book, and where to find things like Jake, to look it up. And that's kind of what we're trying to do here too. You can't expect to know everything, but we do expect you to kind of know where to find it, where to look for it. And there's a lot for you guys, a lot right on this section, this legend right here. There's a ton of real good information. And it's fun if you're an old-fashioned map reader. Oh, maps are fun. But they're like going away. Nobody does maps anymore. I mean, that's kind of the whole thing is we just follow the magenta line that tells you where to go. So, did you? So you like this? That's why I asked you good questions.
I did it. I had to draw the whole world and label the state and the country and each of its capitals for the whole world.
For the whole world. That's fun. See, I used to love that kind of stuff. Map stuff. It shows. It shows. But yeah, this. So we did maps last week, and these are nautical miles, distances, and you see your longitude and coordinate, longitude and latitude numbers in here. And we'll send you home with one of these, and study this. It's real fun. Yeah. Absolutely. And this is the essence of. So what we're trying to do is be able to make a flight plan from 2 points. We're going to go from A to B. Start with, this is called true north, and we've got compass variation. We want to be able to come up with a compass heading. So we start from a course. We want to be able to convert with wind and magnetic variation to come up to it. And you missed that too, baby. What we're trying to do is ultimately for our very final day, we want to be able to pick 2 points. We're going to probably start at like Columbia and go to Monterey. And we've got a lot of things to do. We're going to draw a true course, so it'll be the pencil line. Then we're going to add the compass variation, which lines are somewhere in here. Also, I can't find them. And then we're going to add the wind that's forecast, so we can come up with a compass heading in the airplane that we're steering, get from there to there. And then what kind of airspace, what kind of visibility are we required, who we need to talk to. That's sort of our flight plan. We'll be able to do all of that in 2 weeks. Okay? 2 weeks. Yeah. No, we will. We will. Okay. Fun video. Let's see, which one is this? Is this
This footage shows a terrifying accident from May of 1983. It's an Israeli F-15D flying above the Negev desert with only one wing. The aircraft's pilot, Ziv Nadibi, had just recovered the jet from a tight spiral after colliding with an A-4 Skyhawk and was being ordered to eject. With a runway almost in sight only 10 miles away, however, Nadibi lit his afterburners and headed to attempt a most unconventional landing.
That's a great channel, by the way.
The aircraft. The aircraft involved in the incident was a McDonnell Douglas F-15D Eagle and a Douglas A-4 Skyhawk,
both owned by the Israeli Air Force. Ironically, the F-15 Eagle was created, designed, and assembled in the United States. A sophisticated jet, it's a twin-engine tactical fighter plane designed to fly in all weather conditions. In the late 60s, the U.S. Air Force reviewed several proposals for a fighter dedicated strictly to air superiority. Winning out, the F-15 wasn't initially conceived as an air superiority aircraft. In fact, the design included more, a secondary capability for ground attack. Nevertheless, most operators ignored secondary abilities. Its maiden flight commenced in July 1972, entering service fully in 1976. It's considered one of the most successful fighter planes in the modern era. Since its introduction, models have been exported to American allies Israel and Japan and sold to Saudi Arabia. To date, the F-15 has achieved more than 100 victories collectively and without a single loss of life. Most successes are credited to the Israeli Air Force, however. The Eagle was first imagined during the early days of the Vietnam War, when the U.S. Air Force and Navy competed to discover the next best tactical aircraft. The Air Force quickly adopted the F-15. Thanks to its weight-to-wing area ratio, the F-15 was highly maneuverable. Thanks to its high thrust-to-weight ratio, the Eagle could conduct tight turns without compromising airspeed. It climbed to 30,000 feet in just under 60 seconds. At some speeds, the aircraft can accelerate while traveling vertically. The dynamic thrust output of its engines was even higher than its combat weight and drag, which allowed the aircraft to accelerate without compromising speed. A key feature of the F-15 Eagle is a multi-mission avionics system with a heads-up display facilitating flight use. Other features include an internal guidance system, advanced flight instruments, radar, high-frequency communications, a tactical air navigation system, and several instrument landing system receivers. Amazingly, the plane also conducts electronic warfare to identify friends or foes and implements its own electronic countermeasures. In service, the F-15 totaled a record-breaking 104 kills with no losses as of February 2008. Over half of these were achieved by Israeli Air Force pilots. Furthermore, air superiority models A, B, C, and D have never fallen into enemy hands. Before the accident, the aircraft took down 4 enemy planes during the 1982 Lebanon War. On its second run, it took down a MiG-23 in Syria on November 19, 1985. The plane flown during the practice over the Negev was an F-15D, a 2-seat training version, of which 92 were built between 1979 and 1985. The other plane involved was a Douglas A-4 Skyhawk, a single-seater subsonic light attack plane. Its delta wing and use of one turbojet engine made it notably lightweight, with a maximum takeoff weight of 24,500 pounds. It can fly up to 670 miles per hour. The incident. The accident took place on May 1st, 1983. The Israeli Air Force was carrying out a divergent air combat training session over the Negev region. An F-15D crashed into an A-4 Skyhawk after both planes approached each other too closely and their undersides collided. The Skyhawk plane caught on fire. The pilot immediately ejected. He was able to parachute to land safely. Ziv didn't even realize what had gone wrong at first. He simply felt a big push and saw the fireball caused by the exploding Skyhawk. He heard the radio communication informing the pilot had successfully ejected. The F-15 Eagle began rolling uncontrollably. Its right wing dislocated about 2 feet from its root. Still, both crew members aboard the plane were oblivious. The leaking fuel streamed out of the wing, vaporizing at the wing attachment, which covered their view of the missing wing. Only after descending into a tight spiral did the pilots notice the missing key component. Ziv Nadivi gained control of the aircraft without realizing the full extent of the damage. He switched afterburners on, which at least halted the spin. The 2 crew members were ordered to eject, but opted instead to save the plane by landing it at the nearest airfield 10 miles away. Due to the lift from the fuselage, stabilators, and left wing, the jet remained stable. Nadivi diverted to Ramon Air Base. Suddenly, as he circled to land, the tailhook lowered and descended. The F-15 landed at 260 knots, twice the average speed to maintain lift during a standard landing. The tailhook was consequently destroyed. With high precision and a bit of luck, Nadivi was able to stop the plane only 20 feet from the airfield's barrier. About his decision to land, Nadivi later asserted that he, quote, probably would have ejected if I knew what had happened. In fact, the pilots only learned of their severed wing after inspecting the aircraft upon landing.
That's a tough airplane.
A remarkable repair. The F-15 Eagle with the missing wing, labeled as the 106th Squadron's Marika Shakim, Hebrew for Sky Blazer, was sent to Tel Naf. At the Israeli Air Force Maintenance Unit, it underwent 2 months of repairs. Showing the F-15's extreme strength and reliability, the jet was soon restored entirely. It returned to normal service.
Say $15 million.
Yeah.
So we
Yes, she
developed
would.
that plane and sent it to Israel, huh?
No, they rebuilt it over there. Is that what you said, rebuild it?
No, but we developed that F-15.
Yes, yeah.
And then we sold them to
Yeah,
Israel.
McDonnell Douglas in St. Louis.
Yeah.
Those were all built. They're now called Boeing because Boeing built or bought McDonnell Douglas, but all those were built in St. Louis. And,
How many we selling to China now?
well, we haven't sold any of those to China,
I hope not.
but they steal the information. Seems to get over there. Okay, any other questions? Too early to knock
That was
off.
too full.
Is that okay?
I think there's one more.
Oh, okay. Oh, yeah, this is good.
Jet fuel, 41 and 2.
70 gallons? 68 gallons, Fortis leader.
Stay down at 500 feet to leave fuel for 40-minute fighting time over Dunkirk.
Understood, Vector 128, Angels 25.
And keep an eye on that gauge, even when it gets lively. Save enough to get back.
Dunkirk so far, why can't they just load at Cali?
The enemy had something to say about it.
I don't hear we're setting ducks.
Even field, they'll come out of the sun.
Found it, 11 o'clock.
Right?
He's on me. I'm on him. On my mark, Fortis 2, join left. 3, 2, 1. Clear. Is he down? Yeah, he's down for the count. Fortis leader, one bandit down. Fortis leader, do you know? Fortis 2, I have you got my call. I have no eyes on Fortis leader. Understood, not this one. I'll go for a lick.
Yeah. What's the name of that movie?
Dunkirk.
Oh, that's from Dunkirk?
Yeah, they use real airplanes in that movie, which is pretty cool.
Yeah, they're not doing that so much anymore.
I think that's it.
That it? Okay. Okay, what's next week? Performance?
Yeah, performance charts and stuff like that.
Yeah, if you have, do you have a 172 pilot's operating handbook?
No, but you can get one.
Do we have some random books we can loan out? Most pilot operating handbooks, POH is the term they use. They're not really so thick, but each airplane type has a specific one, and then your specific airplane may have revisions to it for modifications, you know, radios, upgraded engines, you know, alternators versus, you know, there's, each airplane has a manual, so we don't like to take that manual out of that airplane because it's for that airplane, it's an approved piece, so we'll buy another stock one and it'll be a little different. But performance will be things like engine settings, giving you how much horsepower and fuel consumption. Because when we go from our A to B here, we're gonna wanna know how fast we're going, so we can know how long it's gonna take, and how much we burn per hour at our altitude that we select. So that's in performance. So we'll cover that. Taking off on a hot day with 3 or 4 people, can we do that? What's our rate of climb gonna be? That's in performance. So density, altitude, and runway performance. So we're gonna go over that next week. Again, ultimately part of the flight plan for our flight from A to B. We, you know, we're gonna use the runway takeoff, how much we're gonna climb, how high we're gonna climb to, and how much fuel we're gonna burn, all that stuff. No generic ones, okay. Yeah, we don't wanna let this one go, but this airplane's, for this one right here, I mean, it's not biblical, you know, it's mostly pictures, it's really not that complicated on there. A more modern airplane like Cessna 1978, 182 in this case. So it's broken down weight and balance, airplane systems, handling and maintenance, and supplements. But the performance page, you know, is really just is about this much. So the topics would be takeoff distance, rate of climb, fuel burn at different altitudes, and the true airspeed. So if you can find a way to do any homework on those in advance, that'll help. I guess also would be things like this temperature conversion chart, that you figure that out pretty fast. Stall speeds, flaps up, flaps down, and different weights. This would be in the performance section. But for the most part, we're gonna concentrate on this. Takeoff distance charts, and time, fuel, and distance chart, which is actually pretty simple, but you know, you kind of have to, it may affect your plan, but you may do the plan first, say, I wanna go 5,000 feet, and then we go into this 5,000 feet and see what we burn. You know, it's not likely you're gonna say, oh, it burns 1/10 of a gallon more, we better go higher. You know, for that 1/10 of a gallon. Not really in fuel.
You have some leeway there, do you?
Say again?
You have some leeway there, do you?
Yeah, you do. We're gonna pick altitudes. I guess we'll talk about that, how you pick altitudes to fly for your flight. Basically, east is odd, plus 500 feet, 3,000, 5,000, 7,000, plus 500, so if we're going east. But if we're going that way, we're gonna go at 2,500, 4,500, 6,500, or 8,500. So round one of those off to your, to here. And again, you might, when we get our weather briefing, maybe there's a reason to go at 8,000 feet, it's a good tailwind, but can we climb to 8,000 feet between here and Monterey? I mean, you know, we're climbing most of the time and starting down, which it's okay to do. Or maybe we pick another altitude. We'll talk about what altitude to pick.
The way I was taught to memorize that, east is odd, is because out towards the east, they're a little odd over there.
It's true,
So,
yes.
that's
East,
our life.
west is best.
Yeah, west is best.
Yeah, meaning even altitude, so that is true. That's not a, by the way, it's not an FAR, doesn't say that in the regulations, you don't have to pick that, but, you know, you'll see that again on our legend right here. No, it doesn't say having permission, I'm sorry. Yeah, that's correct. But we add 500 feet for what we call visual flight rules, where VFR instrument airplanes pick an even altitude. So they don't tend to look out as much. They're looking at instruments and they pick the even altitudes. A little more incumbent upon us, people that look outside more. So we fly at the plus 500 feet. Yeah, the range, given the amount of fuel that we're gonna have. So yeah, we'll beat that up pretty good next week. And we'll work around, you're flying 172. Dave, you started flying anything?
Not yet.
Have an airplane in mind?
Anything is fine with me.
Yeah, the charts are specific, but they're very common. In other words, the format translates to most airplanes. Okay.
Do you have an idea where you're taking lessons, or
Probably here.
here, like with Jake, or?
Probably, yeah.
Then probably the 120.
Yeah, something like that. We'll sort that out. That's
Good news is the 120 doesn't have a ton of charts. So
there's nothing to read.
We're just overweight.
Yeah. But yeah, there are tons of good. We kind of borrowed from this guy called what was his page? Private Pilot Ground School on YouTube, and I gave him, you know, attaboys and all that. But there's tons of information on YouTube. I mean, you know, just lots of good stuff.
There's so much stuff.
There is. So
You can learn pretty much anything
you absolutely can, and so kind of our job though is we kind of fill in between because there's always some sort of questions.
And
But
this book here is probably the best one. We started with not really following a book, but this is a FAA free book.
Oh, yeah.
It costs $20 to buy this thing through a publisher, but you can get it online for free. And this is the majority of these graphics that you've seen come from there. And this is good to use as your basis for your research. You know, pick a subject and type it into YouTube and watch a couple videos. You know, it makes it a lot easier than reading it. You know, there's not a picture here on windscreen anti-ice.
most of them are real good. Guys put a lot of time, and you know, for not that big of a base, but there's a ton of information. But we kind of lean toward the FAA books because terminology matters.
Yeah,
Their terminology,
that's the number right
they
there.
make
If you punch in that
rules,
number on the FAA
Yeah.
website,
and a lot of
it'll come
the
up.
book manufacturers
It's 20, it's 25.
try to kind of sugarcoat it, make it a little more tolerable. We don't really like that. It's, I kind of like to take, they've been teaching pilots for 100 years how to do it. And, well, they haven't, but I mean, they kind of write the rules.
Yeah.
So we kind of lean toward their terminology. But all of them are acceptable, you know, and you can spend a lot of money buying books. And, you know, everybody's got all these books used somewhere. I mean, they're all around. And again, with YouTube and Internet, all those are good formats to research. But we're kind of trying to stick with their guideline, the curriculum, so we try to cover most everything. But it's doable. All right. Caitlin, any questions? Yeah, okay. You sure
Yeah,
can,
take it.
sure
I
can.
was saying there's a bunch of charts here.
And bring it back with you next week. Bring your map because, when you're working with, because we'll, even though they're out of date, they'll have dates, but, most of what we're going through,
Good for learning.
is good for learning. Okay. Oh,
Do you have an extra section?
oh, is this a terminal? Okay.
I've got a bunch of non-San Franciscos here.
Yeah, take that one. Yeah, yeah, let's see this here. Is this, you got, is this mine?
This is
Yeah.
This is an
Yeah,
older
we're
one.
talking
Take this one,
about,
this is newer.
is this
Heading.
terminal though?
Oh, I'm sorry.
So I got this.
Oh, these are both terminals, okay, yes, okay, sorry, okay, all right, yeah, take that.
Yeah.
But bring them back,
Yeah, it was.
Well, I mean, they're expired, they're not really worth anything, but bring them each week, because
Intense.
wherever we are, we'll jump into that from time to time. Okay? Aiden, any questions?
If you want a chart for a different area, I've got LA, Vegas,
You guys have a chart?
Seattle, Albuquerque, Klamath.
We borrowed, yeah.
Good, good,
Well,
good,
yeah.
okay. And what we covered last week was really, Aiden, read that legend on the back. That's a ton of information, because you'll read a thing, and that'll take you to the internet to
Yeah.
you know, you can't always answer the, you know, when it describes something, it takes you on further.
Yeah.
These are kind of out of date NDBs, but it's good to know what it is. But that airspace we're talking about, we're 700 to 1,200 feet, you know, where G turns,
Oh, yeah.
G turns to E is in here. Obstacles, MSL and AGL know those differences, you know, road, you know, symbols and dams and all that. This is a real complicated one right here. And, you know, in the communications section and nav section, and it's small font for us old guys, but you wanna know what all these are, and these are readily apparent. But lots to know right on that.
Do you guys keep your presentations available, like online at all? Is it
You know,
accessible?
yes, we're, tell you the truth, we gotta admit, we're doing this as we go, we're kinda on the fly here.
Yeah, yeah.
And Jake's been putting them together.
So
He's-
I've been,
I just
I've
wasn't
been,
sure out there if
I've been
you can
videoing
access
it
them.
and putting it on YouTube.
Okay, yeah.
And then, I can send you the Google Drive link, but then each of the presentations put up there, and so you can
That would be
watch
cool,
the
yeah,
videos
yeah,
and all
yeah.
that.
Yes. Yeah, so if you miss a week or
Yeah,
something
so
like
I'm
that.
still
you
that
can
email
re-
thing,
recall
so.
that.
Okay, yeah, I'll
Yeah.
send you a link to that.
You know, we should do.
It takes me a
for you
day or
guys.
two to get it uploaded.
Yeah,
us your
I understand, it's just
email.
kind of a cool
Yeah, I'll
refresher.
give you all my
'cause-
stuff.
Yeah,
Okay.
Well,
but yeah,
yeah,
it's
it's
Let Me
that
Find
day,
Club
so-
We'll do
YouTube,
it for our past classes.
and,
Oh, is that what it is?
yeah, and then as far as the link,
I was kind of hoping if we could keep the momentum going.
Yeah.
Come back and.
if anybody needs that and doesn't have it, let me know, I'll send it out again.
One way or through this.
Yeah, still not quite on the email thing.
Oh, okay.
But yeah.
I
Yeah,
said
yeah,
it's on,
yeah.
I wrote it down,
Yeah,
it should be there.
I didn't send a reminder email out tonight.
Okay, cool.
Go
So,
ahead.
I get it.
And
I get it, but yeah, it's something I'm.
I'm looking at three
gonna
o'clock,
do.
though.
Oh, today's Monday. Yeah, oh my gosh, you know.
Yeah.
And I was doing their conflict training online.
Good.
And that good stuff, I was trying to get in, but.
Garbage got you Thursday?
Yeah.
But, yeah.
Oh, that's fine. Dump the ice in the sink.